Okay, so today we're going to talk about what we call Lewis structures. If you watch the videos that I posted, we talked about that. I'm just going to do a bit of a review and then we'll go straight into the assignment dealing with that. So when we're talking about Lewis structures, basically we're talking about showing for molecules. It can be applied to polyatomic ions, but we won't deal with that in this discussion. It applies to molecules and it applies to basically, or it's a way of showing the structure of a molecule. Basically, oh, I guess I need to share my screen too. Basically, it shows you how the atoms are connected to each other in terms of the electrons being shared and so on. So let me clean this up. Okay, so basically, just to give an example, water, very simple example. The Lewis structure of water can be represented by this right here. And I'm going to explain what this actually represents. So here we have the oxygen atom in the middle, and it's connected to two hydrogen atoms, all right? This line here represents a shared pair of electrons, right? So this is what we call a bonding pair of electrons. And that pair of electrons is basically what holds the oxygen to the hydrogen here, right? The same is true for this line right here. So basically, the oxygen will have two bonding pairs connecting to separate hydrogen atoms. But in addition to the bonding pairs, we have what are called lone pairs of electrons, which are not involved in bonding, but they are on the outer shell of the oxygen atom, all right? So therefore, as far as the water molecule is concerned, well, more specifically, as far as the oxygen atom is concerned, it has two types of pairs of electrons. It has two bonding pairs and two what we call lone pairs. This one and this one right here, right? So whenever you're drawing a Lewis structure for any molecule, it's very important that you make a distinction between both the bonding pairs and the lone pairs of electrons. Now, how do we go about drawing the Lewis structure of a molecule? Well, there are some steps that are involved. I'm going to go through them rather briefly. So let me clear this again. So the first step, and in fact, let me do an example at the same time while I'm doing this, right? So step number one, we get a total count, of the number of valence electrons, all right? Now, how do we do that? Well, it's quite simple. All you have to do is look at the group number of the different elements involved, and those numbers would represent the number of valence electrons, and then you add them up. So in the case of water, right, what we do is we go to the periodic table and we look up the group number of hydrogen, and you'll see that that is 1, but because you have 2 here, you have to multiply that by 2, right? So therefore, the total number of valence electrons contributed by the hydrogen will be 2, right? And then we do the same thing for the oxygen. We go to the periodic table, and if you look up the group number of oxygen, you'll see that it's 6A, right? So therefore, the total number of valence electrons contributed by the oxygen would be 6. And then we add these up. 6 plus 2 gives us 8 electrons, right? And what I like to do when I'm doing this exercise is that I express the number of electrons in terms of pairs, right? So in this case, we have 4 pairs of electrons, all right? You don't have to do that, but that's just the way I like to do it, all right? So that's the first step. The first step is that you determine the total number of valence electrons. I forgot to put electrons here, all right? Okay, the next step is that we arrange, the atoms so that either, and I'm going to do 2 sub parts here, A, the single atom is at the center or B, the atom, let me put or, because it's either one or the other, or the atom that is to the left or down in the periodic table is placed first. Is placed in the middle. So let me write here, is placed at the center. All right, so basically, I hope this is not too confusing, but let me explain what this means. So what we're saying is that after we have counted up the total number of valence electrons, you decide which atom will be in the middle. Now, if there's a single atom, as in the case of oxygen, right, then that oxygen will be in the middle. On the other hand, if there is not a single atom, then basically the atom which is further down and to the left of the other atom in the periodic table will be the one that's placed in the center. So in this particular case, we put the oxygen in the middle and we surround it with the hydrogens, right? And when you join the Lewis structure, we're not concerned about the spatial arrangement. So I could have done this, and that's just as correct. All right. So I'm just going to stick to this here. The third step, number 3, is that we place bonding pairs between the central atom and the terminal atom. So just to explain what we mean by the terminal atoms, the terminal atoms are basically the atoms that are not central, right? So in this case, that would be the hydrogens, right? So in the case of step number 3, remember now we have 4 pairs of electrons to work with, right? So therefore, one pair would go here. So that would be one bonding pair, one of the 4. And then the other pair would go here, right? So that's basically what we do in step number 3. And then in step number 4, we place, how should I put this? We place remaining electrons, maybe I shouldn't say remaining, but let me go with that. Remaining electrons on the terminal hydrogens or terminal atoms, right? Excepting, and this is very important, excepting hydrogens, all right? So what we're saying here is that in step number 4, after you have assigned the first 2 pairs bonding electrons between the oxygen and hydrogens, then what you'll try to do is put other pairs of electrons or the remaining pairs of electrons on the terminal atoms. However, in the case of hydrogen, we cannot do that. And the main reason why is because hydrogen cannot have more than 8 electrons on its outer shell. I think we discussed that last time, if I'm not mistaken. But if not, then just accept this as gospel, so to speak. Hydrogen atoms cannot have more than 8 electrons on its outer shell. So what does that mean? That means that the next step, step 5, if I can squeeze it in here, is that any remaining electrons will be assigned to the central atom. All right. So that means that in the case of water, remember now we use 2 bonding pairs here and here. We cannot put any more electrons on the hydrogen, which means that the other pairs of electrons will go on the oxygen, and therefore that would be the Lewis structure for water. All right. So those are basically the general steps. Now there's some additional steps which I'll explain later on, especially when it comes to multiple bonding. But one thing I want to say here before we leave this example, and that is that we try to make sure as much as it is possible when we're drawing these structures, we try to make sure that all the atoms have 8 electrons on its outer shell, right? Excepting hydrogen. Hydrogen can only have a maximum of 2, but oxygen and nitrogen and other elements can have up to 8 electrons. And in fact, some other atoms can have more than 8, but we won't get into that as well. I think that's a bit above our discussion right here, right? So if you look at the oxygen here, right, you see that it has 2, 4, 6, 8 electrons, right? So therefore, we are satisfied that this would be the structure. And of course, each hydrogen can have a maximum of 2 electrons, which we have here for this hydrogen and here for that hydrogen, right? So therefore, as a result, we can say confidently that this would be the Lewis structure for water, all right? Okay, now any questions about this before I move on? Any questions? Any questions? All right. So let me move on now to another example, maybe a bit more complex. Suppose you're given, I want to give an example which is not in your assignment. Let me see. Oh shoot, I should not give, anyway, that one is fine. Let me see. All right, suppose I gave you SCl6, all right? And I'm going to go through the same steps as we did in the case of water, all right? So the first step, if you look at your notes, if you copied what I wrote down, the first step would be, right, so how do we do that? Sulfur, what's the group number for sulfur? No? Well, oh, I'm sorry. Okay, so that's a newer version of the periodic table. The older version, which is what I'm accustomed to from high school, so you can guess my age based on that. But the older version would have, let me explain here. This would be 1A, this group here, 1A, then 2A, and then you come over here, this would be 3A, then 4A, then 5A, then 6A, then 7A, then 8A, so it would be 6. So therefore, in the case of sulfur, yes, it would be 6, all right? So sulfur will contribute 6 valence electrons. Okay, so sulfur will contribute 6 valence electrons. And then what about the chlorines? 7, but there are 6 of them, right? So we have to multiply that by 6. Excuse me, so 6, 7 is 42. 42 plus 6 is 48 electrons. And as I said before, I prefer to express them as pairs, right? So this would be 24 pairs. So the next step is, okay, so how would you do that in this case?
That's in the center, right?
Exactly. Exactly. And then you surround it with the chlorines. And you know, you don't have to be exact in terms of how you surround it. So I'm just going to do this here, and then I'm going to put one here, and then I'm going to put one here. It doesn't matter how you spread it out, all right? Because we're not concerned about the actual shape of the molecule. We just want to show how the atoms are connected to each other. Okay, so we have 24 pairs to play with, right? So what will be the next step? Bonding pairs. So 1, 2, 3, 4, 5, 6. So we have used 6 of the 24 pairs so far. So what do you think we're going to do in the next step? We're going to start doing what? Putting dots, right? Around where? Around which atoms? All the terminal ones. Right, exactly. So you're going to put, now remember, the aim is that each atom will end up with 8 electrons on its outer shell. So this is how you're going to do it. You're going to put 2 here, 2 here, 2 here. That has 8. And then you do the same thing here, same thing here, same thing here. That has 8. That chlorine has 8. So far, I've been losing count. So 6, or let me use pairs. 3 pairs, 1, 2, 3, 4. So that's 12 pairs so far. Then, hold on, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so we have 12 pairs so far. The 13th pair goes here, the 14th goes here, 15th, 16th, 17th, 18th. I have a funny feeling I'm doing something wrong. 1, 2, 3, 4, 5, 6, 3's 18. Yeah, this was a poor example for me to choose. I mean, not that it would be incorrect, but so we have used 18 of the 24 pairs. I have a sneaking suspicion something is wrong here. 1, 2, 3. Oh, my bad. I forgot the bonding pairs. So basically we're done because the 16 plus is what am I saying? It's 6 plus 18 pairs gives you 24. So therefore, this will be the final answer right here. All right. Now, the reason why I said that this was a poor example, not that it's wrong, is that I was telling you that, you know, all atoms should have 8 electrons. The sulfur here has more than 8. 1, 2, 3, 4, 5, 6. That can happen, but that's beyond our discussion for this class. But, you know, the steps that we went through is basically what I'm trying to emphasize here. All right. Okay. Any questions about this example? Any questions? All right. Now, what we're going to do now is look at an example where we have multiple bonding. And basically, let me just, you know, give a little introduction. You can have situations where you have one pair of electrons being shared between 2 atoms, such as hydrogen. In the hydrogen molecule, we have that arrangement. But you can also have a situation where we have 2 pairs of electrons being shared between 2 atoms. Now, one example of that would be oxygen. This here I'm drawing is a Lewis structure for the oxygen molecule, right? And then yet there's another situation where you can have 3 pairs of electrons being shared between 2 atoms. And an example of that would be the nitrogen, molecule, right? So this here I'm drawing is a Lewis structure for nitrogen, all right? So this bond we call a single bond. This bond we call a double bond. And this bond here we call a triple bond. All right. So we can have multiple bonding, in other words. In fact, there's one step further. You can actually have, believe it or not, a quadruple bond, but that is like, you know, graduate school stuff. So I won't go into that. All right. Okay. Now that's important in determining the Lewis structure of certain molecules. And one example I want to point to is carbon dioxide. So are you all finished with this here? All right, so let me get rid of this here. And then let's start off with carbon dioxide. So that's the formula for carbon dioxide. And we're going to go through the same steps, but there's one additional or maybe 2 additional steps that we have to take. So let's start off with the first step, which is, okay, so carbon will contribute how many?
5.
Carbon is in group 4A. So it will contribute 4. Oxygen will contribute how many? 6. But because you have 2 of them, you have to multiply that by 2, so that gives you 12, right?
It's 4 and 7, so why is, oh, never mind.
Yeah, oxygen is,
I misread it.
yeah,
This part's gonna confuse me.
yeah, right. Personally speaking, I prefer the older version of the periodic table. And I don't know what, in the periodic table that I've posted in Canvas, I have 2 versions of the periodic table. And the reason why I have that is because one of them has the older, right, exactly. Okay, so We add these up, that's 16 electrons, which is equal to 8 pairs, all right? So we put the carbon in the middle and we surround it with oxygens. Again, it doesn't matter how you surround them. So what's the next step? Okay, so we're going to use 2 of the 8 pairs. One will go here and the other pair will go here, all right? Then what? Right, so around the oxygen. So that's 3, 4, 5, 6, 7, 8. All right. Now, if you look at this structure carefully, you'll see that the oxygens are okay in terms of its octet, right? Each oxygen atom has 8 electrons, but the carbon does not have that. Carbon has 1, 2 electrons, right? So this will not be the final structure of this molecule because the carbon is not satisfied. So how do we solve that problem? Well, we push 2 of these pair of these electrons to form an extra bond right here, and another pair of electrons will come here to form an extra bond right there. All right. So in the final answer, this will be the Lewis structure of carbon dioxide. And now carbon has 8 electrons, all right, just like the oxygens. All right, so those are situations where you can have multiple bonding taking place, all right? Any questions about this? Any questions? All right, let me see if I can give another example and then I'll get you started on these here. Is it okay for me to erase this or are you still writing? All right, so let's say you're given, I want to make sure that I'm not messing up on this one here. Let's say you're given okay, let's say you're given CH2O. All right. So in this particular case, the question now becomes which one would go in the middle? Now you have carbon here, which is 1 atom, oxygen here, which is 1 atom, but carbon in relation to oxygen is to the left in the same period, right? So I will put the carbon in the middle, and then I will surround it with the other atoms. And again, it doesn't matter how you place them. So you can place a hydrogen here, you can place a hydrogen here, you can place an oxygen here, all right? And then now you have to put the bonding pairs, right? Oh, before that, I missed a step. What's the step I should have? Yes, so carbon will contribute 4 electrons. Hydrogen will contribute 1 times 2 equals 2, and oxygen will contribute 6. So when we add this up, you're going to get 12 electrons, which is equal to 6 pairs. Okay, so what next? We start out with the bonding pairs, right? 1, 2, 3, 3 bonding pairs. Then the question now becomes, where do we put the extra electrons? Well, we cannot put it on the hydrogens because the hydrogens cannot have more than 2 electrons on its outer shell, which means that the remaining 3 pairs of electrons will go on the oxygen. And again, if you look at the structure, you see that the carbon is deficient in terms of not having 8 electrons. So how do we solve that? One of these pairs of electrons will go here to form an extra bond. So therefore, the resulting structure would be that. All right. So that's basically what's involved in drawing the Lewis structure based on the formulas for these compounds. So with that said, starting on these, and if you have any questions, of course, feel free to ask. That's what I'm here for.
I have a question about that. Did we ever figure out what was going on with the exams? I still wasn't able to get on there. We weren't able to either, right? We were talking about it. And I noticed by like Thursday, I'm like, well, I'm not gonna get it by now, so I'll still come someday.
All right, tell you what, let me call him again.
It's still just the same thing. I'm like.
Uh.
I don't know what to do.
Okay, I called them today. I'll let you know what's going on.
Beautiful.
Yeah, I've heard that.
Yeah. Oh, okay. Thanks.
Thank you.
Mhm. Yes, sir.
Is this Cl2 or is this carbon and iodine?
No, this is oh, yeah, that should be, yeah, that should be a subscript. So Cl2.
Cl2.
Yeah, exactly. Mhm. Finished?
I'm finished.
Okay, I forgot to mention it while she was here, but make sure that I've posted some new videos this morning
Okay.
in the module section for chapter 4. So, and I need to post some more, but at least watch the ones that I have for now.
Okay.
I'm gonna post the others either tonight or early tomorrow morning, depending on how much sleep I get. Mhm.
I'll keep,
And then, yeah,
checking every day about that.
yeah, I'm gonna call over there today, definitely.
I will see you next week.
Alrighty.
Thank you very much.
Mhm.